Okay, so we're going to start off by putting a poll in the chat, and if you guys could all put what answers you would like to go over, then we'll go from there.
You can pick as many questions as you'd like to have gone over as you want. So if you want to go over all of them, I guess pick all of them. It's multiple answers. So
yeah, and we'll just start at the one that has the most answers and then go from there. All right, so it looks like the number of votes is more or less stabilizing, and we're going to have Gabe go over the first question, and then after that we'll alternate in going over questions.
yeah, all right. So I will get started. It looks like, yeah. So the poll says we have 14 votes for don't care. There's actually a pretty wide distribution, it looks like. But besides that, the most requested question was heap flattening. So that's winner 18, question 27. So I will, I'll start presenting. And all right, so hopefully you guys are able to see this. And we'll go all the way down to, looks like it's the first previous exam question. So yeah, so for flattening a heap, did anyone want to like throw out some ideas that they had for how you would do this? I mean, the problem statement, I guess I should say first, is you're given a heap, as we talked about in class, and we want to convert this heap into essentially a linked list where instead of each node having 2 children, each node just has a right child, and it still has to maintain the same ordering as the heap had, in the sense that, you know, you basically, we talked about kind of how you read a heap from top to bottom and left to right, like kind of like a book, right? So the ordering is like 83, 66, 78, then the 19, 20, 75, and 49. And then, so you want to maintain that ordering, except you want to just have it as one single linked list. So with that, I guess now I'll get into the question. Does anyone have any ideas or thoughts on how they might approach this? Okay, yeah, so we got some pretty good ideas in the chat. I see several people saying BFS, which is actually something that we cover later in the semester. And that's exactly right, though. So people are saying Q, people are saying BFS. Those are really the same idea that you guys are putting out. And although we don't cover BFS, which stands for breadth first search, until later in the semester, this is very, very similar to what you guys did in Project 2 when you implemented several of the pairing PQ functions. So you recall that with the pairing PQ, you would essentially put all of your nodes into a deck and then just pop from it one by one. And that would essentially look at every node in your heap. So this is also a valid thing to do for a binary heap rather than a pairing heap. And by putting it into a queue, you can basically look at every element in that order that I talked about, left to right, up to down. So yeah, you guys are totally right with the idea of using a queue. Someone put out recursion, and that's a good idea. It wouldn't work in this case though, because it wouldn't exactly look at the nodes in the correct order. So using recursion is actually very much analogous to pushing everything into a stack and then popping from the stack in order. And that's what's called a depth first search, or DFS. But unfortunately, that won't produce, or that won't be quite as easy to work with as if we were to use a queue. So anyway, if we read the rest of the problem statement, we see that the right pointer within each node must be used as the next, and the left should be set to null pointer. So this is good. We're essentially just creating a stick instead of a binary tree or a binary heap like we have here. So Cindy asked, should this be a priority queue or just a queue? Just a queue in this case. You want to just maintain normal FIFO ordering for this. So you guys are totally right. What we want to do first is probably make a queue of these node pointers. So we have queue of node pointer. So, and then what we're going to want to do is just keep iterating through this queue and making this list. So for each node that we put into the queue, we're going to want to push its children into the queue and break those connections. And then we're going to essentially remake those connections. So first we want to put 83 into the queue, right? So we're going to say, we're given the node pointer to the binary heap, which is essentially the root of the heap. So we're going to say q dot push and then we're going to break the connections to that binary heap, right? So for that, we're going to say or sorry, we're not going to break those connections yet. We want to do that in the loop, because otherwise we won't have access to its children to push it into the queue. So what we're going to do is going to say while not q dot empty, we're going to say, so what we want to do now is say if the queue has children, then push those into the queue as well. So if, or actually we'll first declare a variable to make the writing a little bit simpler. So we're going to say node and then now that we have the front node, we can just push its two children into the queue and pop it after that, and also break the connections of that node. So what we're going to do then is push both of its children if they exist. So if and we have, and if we go back to the structure of the node, we have a value and a left and a right. So if n left, we're gonna push back the left. Oops, not push back, just push. Oh, and I also neglected to say n left here. So, right, well, do we have any questions on what's going on here? I know you guys might not be super familiar with breadth first search. So yeah, you definitely, it might be a little bit tough because the only real exposure you guys have had to this would have been project 2, where you kind of use this idea for the parent PQ. So are we good with what's going on here? Yeah, okay, right. And then after that, we're gonna wanna make sure to pop, of course. And finally now, we can essentially just append the current node that we're looking at to the end of our linked list. So how are we gonna make sure that we're appending to the very end of our linked list? This is an open question. I'm wondering if you guys have any ideas. Yeah, so append it where node at next is a null pointer, that is the end, correct. And then another person, Lydia, was saying, use a separate pointer to keep track of the linked list. So I think that's the right idea. So you guys are both correct. Of course, it would be a little bit inefficient to look at where the next is, where the node's next element is a null pointer if you were to do that manually at every iteration, because I mean that's an O-Ven operation, right? You would have to look through the whole linked list until you get to the null pointer. So alternatively, I think it's most efficient to keep track of where that end node is and essentially just update it through every iteration. So because of that, we're actually probably going to have to declare a new variable at the top here. So I'm actually kind of running out of space here, but hopefully I have enough room. So I'm going to declare this node pointer called last. And using that last node pointer, I'm going to be able to push, or really append this next node at the end of our queue, and then I'll update it every time. So now that we have this node, we can just push it to the end. So of course, on the first iteration, though, we have to make sure that because last is a null pointer, we want to keep track of. We don't want to dereference a null pointer at the first iteration. Is all I'm saying. So essentially, last. Then last at right equals n, right? And then otherwise we don't need to do anything, right? Because we're not really we just need to update last, and then we do that in either case, right? And then so in either case we just set last equal to n, and then want to make sure that n's left is null pointer, because that's what the problem statement said. We're essentially updating every right element to make our linked list, and then setting every left element to null pointer. So we can either do last at left equal null pointer or n at left equal null pointer, same thing, because we've just updated last. Okay, and then I believe that should do it. I could be missing something because I'm doing this on the fly. But this is the idea here. So yeah, we don't need to return anything. It's a void function, so we don't need to keep track of the first element or anything. And you can see that as you go through this, you will be setting every node to the end of the linked list, and the left of each of those nodes that you add is going to be a null pointer, and that's basically the functionality we want. So yeah, I hope this makes sense. I'd totally be willing to kind of walk through a short example of how this would actually work on paper, like just draw it out a little bit. If anyone would like me to do that, please say in the chat or on the mic. Yes, I have 2 yeses, 3 yeses, so that's good enough for me. And quick question from Justine, what's the line after last equals n again? That's n at left equals null pointer. So you recall in the problem statement, it said the left must be set to null pointer right there. So that's the only reason I do that. Okay, so yeah, so I guess I'll draw it in green off to the side here. So I probably don't want to do this whole tree. I guess I'll just pretend that the tree is a little bit smaller. So I'll ignore these elements just, to make it a little simpler. So, okay, if we have this tree, 83, 66, 78, 19, we're going to want that to become this, right? So the way we do that is we make sure, oh, I think I did forget one very small thing, and that would be n at right equals null pointer. So the reason I say that is because we have to make sure that the very last node points to null pointer. So the only reason I do that is at the end we have to make sure that, yeah, this 19, for example, would point to null pointer. So small thing, but same idea. Anyway, back to the example. So we have, what would we do first? We make this queue called, so we're going to say Q just has 83, right? Because we push the binary heap to it, and then we're going to say, what is last at this point? Last is just, it's undeclared, really. So technically, it's not null pointer. I'm going to just call it null pointer for now. And then, so while the queue isn't empty, we're going to say n is equal to q.front. So n is going to be this. N is also going to be 83. And then we're going to say, if it has a left, push the left. If it has a right, push the right. And if we go back to this drawing, we see that 83 has both a left and a right. So we're going to push 66 and 78. Okay? And then from there, we're going to pop from the queue. So we're going to get rid of the 83. And now we're going to say if last, then last at right is equal to n. Otherwise, last is just equal to n. So we don't do that if, right? Because last for now is undefined. Actually, you know what? I probably should have set this to null pointer just to be a little more explicit. But again, a small subtlety that you wouldn't lose points for. And then, so yeah, we're going to end up setting it to the 83. And what's last in our code? We have to make sure n at left is null pointer, which is really last at left, and n at right is null pointer, which is really last at right. So we have 83 pointing to null, and then its left is also null, which I'm actually not going to write out because, oh, I will. Move this a little bit. Right, so this is its left. This is, I'm drawing the right a little bit like straight to the right to kind of emphasize that this is a linked list. But yeah, so we have the left here and the right here. Okay, second iteration, we have 66, right? So we get the 66 and assign it to n now. So this is now 66. And if it has a left, push the left. If it has a right, push the right. We see that 66 only has a left. So we're going to push the 19. Okay. And what's next? We pop from the queue. I already did that. And then if last exists, then last at right equals n. So what does that mean? That means that we change this null, which is currently last's right, because last is 83. Last is currently 83, and then so we're going to change its right to this item that we just popped, which was the 66, right? So we're going to do this. And then finally, we're going to set last equal to this element, which is good. And then I'm going to set so really it would probably be a little bit more sensible to call this the whole list, and then just point separately to the last. So I'll do that with blue. So I hope you guys are following this. So this is just, I want to show the whole list and just show exactly where the last pointer is. So we're going to update the last, set the last left and right to null, and move on. So I'm going to go a little bit faster now because it's really just the same idea. So what we do now is we get the 78. We see that in this example, it doesn't have any children. So we're just gonna go to the next part of the while loop, which is to pop it. So we pop the 78, and then we see that last is indeed defined. So we're gonna set last's right to the 78. And finally, we need to make sure that we update the left and right, and also set last equal to n. So setting last equal to n is going to look like this. And updating the left and right is going to look like this. All right. And the last part with the 19 is going to look the exact same. So I'm going to move this over because I'm once again running out of room. And so I'm not even going to really walk through the code for that. Just 19 is going to get popped, and it's going to get put here. It's going to point to a null element here and a null element here. And I actually didn't update the n for the 78 example, but yeah, should have done that. Again, I was going through it relatively quickly. And So last is going to get moved to here. Okay, I hope you guys were able to follow that. And I hope that actually walking through the example kind of helped you guys better understand what was going on with this process here. Does anyone else have questions about this? Jonathan's asking, are we going to be looking at your code or is it graded by the autograder? We look at your code. So the autograder, we just are going to use to kind of gauge if it's right. It'll help us a little bit in terms of just efficiency with grading the exams, but it is going to be completely hand graded. Yep. How do we know for sure that left is always null? So do you mean the left element of everything that we put into our list? So like, I guess, these guys?
Yeah.
Yeah, okay. So we know that because we explicitly said it that way. So you saw at this, it's this line in particular that makes sure that happens.
Like, was it given in the prompt to set left to null pointer, or is that like something we're just supposed to like do?
Yep, that'll be this part right here.
Oh, sorry, I couldn't see the top. Thanks.
Yep. Shouldn't we check first if binary heap is empty? Let me think about that. I don't think you would have to. That's a good subtle thing, I guess. So if it's a null pointer, you're going to end up pushing back a null pointer. And I think you would, so you set the left and the right. And then you'd say, yeah, so yeah, you are right, because at the very end here, you make a very good point. That's a small subtle thing that I missed. We're going to be dereferencing the node here, and I guess here and here too. So yeah, if binary heap is equal to null pointer, you can just add a check. I guess I don't have room here, but yeah, if binary heap, or if not binary heap, which is the same as if it's equal to null pointer, then return. Yep, that's a good point. You would totally cite fault if it's empty, and that's, I guess, a small case that you would account for. But you definitely wouldn't lose many, if any, points for missing that. Could we just set n at right to queued up front? Yeah, I believe you could. Okay. I think we might be okay to move on to the next one. Yeah, I think if there are no more questions on this one, I'm going to hand it off to Eleanor so she can talk about the next most requested question.
Yeah, so it was actually a tie between several questions. A lot of them were all at 5%. So I decided to go with the question that is the one that is about sorting student IDs. So that's Winter 20, question 27, because I think that question highlights a couple important strategies that could be useful on the exam. So I will start presenting. Okay. Okay. So the question is asking if you're given a vector where it's not, it's not sorted, but it's also not like totally in random order either. You know that every element is at most d from the position that it's supposed to be in. It's asking you to sort it in n log d time with O of d auxiliary space. Do people have any initial thoughts or ideas that they want to put in the chat? Just like throw whatever ideas you have out there. It's okay if it's if you're like unsure about it, just put it out there. Yeah, so we will use some concepts of merge sort in that we can sort it by only looking at a small chunk at a time and sorting that small chunk. Yeah, that's right. We can sort within like the positions of your current index that you want to find. This problem is also kind of similar to the needle and haystack problem mentioned in lecture 13 about strings and sequences, because in that case, we just have like, because that used what's called a sliding window strategy, and there we only look like at a small portion of it, and we just move that portion that we're looking at it over by just a fixed amount each time. Yeah, so I'm going to start writing out a solution. There's actually a couple solutions to this, as you'll see when the solutions are released. I think I'm just going to pick one to go over in the interest of time, and then the other one you can look at on your own time once you get the solutions packet. So the problem with this is that you can't just automatically apply any of sorry, there's a question in the chat, would insertion sort also fit the time? And you can't just like directly apply any of the sorts that we learned about because those sorts would have n log n time, and it's asking for n log d time. So the idea here is that we apply some principles of the sorts that we've learned, but apply it to a smaller section at a given time. And yeah, so I think so solution, yeah, okay. I'm going to go over a solution that is the solution that's the most similar to the ideas that people have been putting in the chat. And so, sorry. So we're going to start by, so for this, like people mentioned, we can sort like a smaller portion at a given time. And for that, you would totally be allowed to use the standard sort function, which has complexity of whatever input size, like say m, so m log m. And to use the standard sort, you would want to put in begin and end iterators. So I'm just going to start by saying, by setting, I'm just going to start by setting one iterator to be the beginning of your IDs vector. And we're going to go through the vector, and at any given point, we're just going to be looking at a window of size 2 times d, because we know that any element is going to be at most 2d from its given position. So for example, the element that goes in the very first position is going to be at most, in the example, 2 places from the first place where it should be. So we're going to set the back iterator of the place that we're going to be sorting 2D places from the front iterator. And now we just want to go through the vector. The next thing to do is figure out how many iterations it will take. So because the idea here is that we have a window of size 2 times d, and we sort that window, and then we can move the window forward by d, because everything that is in the first half of that window, so the first d elements in that window, will now be in their correct place, because they were at most d places from where they're supposed to be. So then we can move forward by d each time. Now for moving forward by d each time, we need to figure out where we're going to be ending. Oh, and I forgot one thing. I think we would also want to add in a check to see how 2 times d compares to the size. Because if d is bigger than, say, half of the size that you're given, then that means that really the elements could be anywhere. And in that case, you can't do like this whole sliding window like I mentioned, because the window is bigger than the size of the vector itself. So first you'd want to add in this check to see if d is less than the size. In that case, now we're going to iterate through. And I'm going to say for and so now if we're iterating through by d each time, do people have sorry for not checking the chat as much. I was focusing on writing out the answer and talking through it. So there's a question that's asking why 2 times d and not just d. Yeah. So like Gabe said, the idea is that like we want to be able to take into account the window at any given point as we're going through, not just what's convenient at the very beginning. Do people have thoughts on there's a question, can your for loop conditions be based on the iterators? Yeah, I think they could. I think for now I'm just going to use indices because I don't want to make a mistake as I'm translating it from indices to iterators. But yeah, you can totally use iterators as well. That just goes in general. Elizabeth is suggesting while back does not equal the end. Yeah, and I think the idea here is that I think one thing we want to make sure is that like the size is not necessarily going to be exactly divisible by d. So if we're like moving forward by d each time, we want to make sure that like we don't go past the n too much because that's undefined. So here we want to figure out the number of times that we would need to go through. And so if we're incrementing by d each time, then you could take the size and divide it by d. There's a question, what do you do insertion sort to sort the first d elements in the 2D window? Yeah, so we'll get to that. How do we just know to use window sliding sort since it wasn't covered in lecture directly? I think the concepts of having a window that you're going through, that was covered in the strings and sequences lecture when we're searching for a needle in a haystack. And so you could take a look at that if you want to review the concepts of window sliding. I think as for knowing that you're looking at like a window of that size, the key here is that everything is going to be at most d positions away from its current sorted position. So then that means that you can look at a window of that size. And I'm going to set my n condition as the size of the vector divided by 2, and I'm actually going to have an extra factor of -1, and that, and I think I'm not going to explain why that is right now, but I think it'll be made more clear when we go through the solution. I think it'll be a little tricky to explain that right now. Okay, so now we have our window of size d. We're going to sort. So here we're using standard sort, and we're passing in the begin iterator and the end iterator. Remember that the begin iterator is inclusive and the end iterator is exclusive. So this will sort the first 2D elements exactly. And then now we can just increment front by d and back by d. And so yeah, so I remember it being mentioned earlier that you could say like if back does not equal end, but the problem is that if we're incrementing by d each time, we're not guaranteed to like hit the end exactly. And so now we're going through, and so at any given point we have our window of size 2D. We're sorting that window, then we're moving forward by d, and we're sorting that next window, and then we're continuing that until we reach a point when if we tried to increment anymore, we would go off the end of the vector. So we want to always make sure that our back iterator is still less than the end.
Eleanor?
Yeah.
Did you mean divided by d or divided by 2?
D, yes, sorry.
Yeah.
Thank you.
Yeah.
Yeah, and I think so. I think for why it's id set size divided by d minus 1. I think I think I'm going to go through the example and make it more clear. I think, and then it'll make more sense then. I think so. I think like say you got this problem for an exam and you're writing it out. I think your first step probably would be just take the size and divide it by n. But then if you like then you like take your code that you write down and then you try running through the example with it, and you'll see that if you do just n divided by d, then you would end up going off the end of the vector. and then the fix for that is subtracting 1. But I'm going to hold off on the explanation until I finish writing the code and we can go through the example. Yeah, so at this point, we've sorted the first, I guess we sorted elements up to, trying to think of the best expression for it. So if n is not exactly divisible by d, then you would take like the number that's like a little bit smaller than n that's divisible by d, and we've sorted up to that point. And now, now we can just sort the rest of it by saying sort front and this way you guarantee that this takes care of the case where if you were to increment back by d at a given point, you would go like past the end of the vector, because IDs.end always points just past the end. And so now I'm going to go ahead and go through the example, and and I think that will help the code that I wrote make more sense. So we start with front pointing to here, and actually let's change colors. We start with front pointing to here, back pointing to here, but and then we would sort these elements. So then we wind up with 1, 2, 3, 5. And notice here that 1 and 2, since they are both guaranteed to be at most d positions from where they're supposed to be, that means that when you sort them, they're guaranteed to be back in the right place. And then now we move our iterators forward by d. So now we have front pointing there, back pointing there, and now we're sorting this region, 3, 5, 7, 9, 4, and then that would give us, and actually I should have written the rest of the vector. So then that gives us 1, 2, 3, 4, 5, 7, 6. And so now 3 and 4 are back in the correct place. And now, now if we try to, so here we have n is equal to 7, d is equal to 2. N divided by d then would be 7 divided by 2, which is 3 when you round down. And notice that we've run this loop 2 times so far. But if we were to try to increment it one more time, we would have 1 pointing to here and back pointing to like somewhere like past the end of the vector, and we don't want that. So then we would want to just go to n divided by d minus 1, and so we only do our sliding window that many times. And I think this is because our window is of size 2d, not just d. And so like I think by saying minus 1, then that ensures that our back index is always either like within the vector or just like, yeah, the integers are back vectors always within the vector. And so at this point in our for loop, we've reached, we set our condition in this particular case to be and we've to be 2, and we've done it 2 times now, and so now now we had so now we have front pointing to 7, back pointing to somewhere past the end, and we exit our loop and we just sort this remaining part of 7 through, am I missing something? 1, 2, 3, 4, 5, 6, 7. Oh yeah. So here, front is pointing here, and back is pointing somewhere past there. So then we would just sort this remaining part 7 through the end and get our sorted vector. And then if it so happened that d was, that 2 times d was greater or equal than the size, so what if we had a d of 4? In that case, we had front still equal to IDs dot begin, and then so then that would just be sorting IDs dot begin and IDs dot end, and that just sorts the entire vector. And here d is approximately is about like, it's on the order of n divided by 2, and so then that complexity still works out because it's still n log d time. Yeah, so I'm sorry, it's hard for me to do. What outstanding questions do people still have that haven't been addressed in the chat? If you could type it again or unmute your mic, because I'm not quite sure which questions have been answered and which questions weren't.
I think the big one, Eleanor, was where the -1 came from in the for loop. So for the end condition of the for loop.
Okay, yes. So I think, so let's see. I'm trying to think of the best way to explain. I think, so this example showed that the -1, that you can't, this example showed that you can't just have n divided by d, because you might end up going off the end of the loop. But then the question would be, how do you come up with -1, and how can you be sure that it works for any given n and any given d? So I think you start off, so if you're starting off with back at 2 times d, and you want to make sure that back is always less than n, and you know that you're incrementing back by d each time. Then your question is, how many times can I add d to back and still make sure that it's less than n? And then you can add, obviously for one time you can just start, you can add d 0 times, and that's the first time that we're going through the loop. So let's say, so now we want back to be less than n. Really we want back to be less than the value that's like, the value that's closest to n. Yeah. Okay, let's say that let's make k the number of times that you can multiply, the number you can multiply by d and still get something that's less than n. And so then when we're saying that we want back to be less than n, yeah, I'm sorry, I'm I'm putting together this explanation on the spot. Yeah, so I think we have back, we have 2 times d, and we want to add it like a certain number of times, say like j times, and still get something that is less than n. And we can, so then that translates to n divided by d, and then that means that we want to add d to the back index at most n divided by t minus 2 times, and that's the number of times that we can add d. But then for our for loop condition, we can also run our for loop 1 time when we're not adding d at all, and so then that gives a condition on I where it's I is less than, where you can run your loop that many times. And yeah. Let me know what other questions you have from that. So that's okay. So if you have so I'm kind of running out of space. If you have okay, so if d is, let me just say d is greater than n divided by 2, then yeah, so the question is, like, by just doing this sort, it looks like we're doing an n log n sort, right? If so, let's look at the case, like say d is exactly n divided by 2, in which case we would still go to this condition. D is equal to, oh, sorry, I don't know what I did just there. Then you have your sort is going to be n log n, which is the same thing as n log 2d, which because for asymptotic complexities, the constants don't matter as much. That's still n log d. And I think the key here is that when if d is greater than or equal to 2n, then that means that n is less than or equal to 2d. So when you have a sort of that's of complexity n log n, that's also a sort of complexity n log 2d, or something less than 2d. So that comes out to complexity of d in the logarithm. What other questions do people have? And let me know if you want me to repeat or clarify something that I said already as well. And then also, I will say that this is not the only solution, possible solution I think as was mentioned earlier, you can take a look at the other solution, and so like if you didn't come up with like this exact thing, the other solution I think is not quite as fiddly when it comes to like the start and end stuff. So it's okay if you don't come up with the solution exactly like this. You can take a look at the other one, and hopefully that one will also make sense.
To give a flavor of the other solution, at least the other one that I know about, definitely the other solution is what I thought of when I first looked at this problem. And that would be to have a priority queue, actually. So you maintain a priority queue of size D and just pop from it every time. So it would be a min PQ, and you're popping from it every time and inserting that at your current index, right? If there's a lot of demand to talk about that, we can get more into it, but that's just the general idea. If you guys want to talk about that more, say it in the chat. Otherwise, we'll move on to the next one probably. It seems there is some demand.
I'm not, yeah, like part of me wants to go over the solution because it's good to talk about a priority queue solution. The other part of me is like, then that means we might only end up talking about 3 written questions
Yeah.
in the entire review session. Keep in mind that the solutions for this entire packet will be released shortly after the review session ends.
Yeah, maybe Eleanor, like talk about like just graphically, like on the
Okay.
just scribble over the IDs vector and talk about how that will work.
Okay. Yeah, I can do that. Okay. So, oops, sorry. Yeah, so the idea here is that you would put, so for D equal to 2, you would put these elements into a priority queue. And so this ensures, so you know that 1, the element that goes in this place is at most D places from here. So the farthest that it can be from the position that it belongs to is here. So then you know that this priority queue containing 3 D plus 1 elements is always going to contain the element that belongs the element that belongs in like the leftmost place. So then from this priority queue, we can pop the min element and put that as our first element. And then we add the next element, and we took out that one. Sorry, that's getting a bit messy. So now I should write it out on the side. I should have done from the beginning. So we had our priority queue of 2, 1, 3. We took out the 1, and we put it as our first element, and then we added the 5. So then this ensures that whatever element belongs in this place, it will always have been, like, it can be at most at that place far away from it. So then this priority queue will always include the one that belongs at this place. And so then again, we pop the min element and we put it in its proper place. And then we add the next one. And then you keep going with that until you get, let's see, so if you're, I think you would end with priority queue that has, I think, these elements. 1 sec, so yeah, because I think you would end this particular loop after you added the element that belongs here, because you took out, at that point you took out the minimum element 4 and then you added 6 into your heap. So that would have 5, 7, 4, then you would have taken out the 4, added 6. So you would have a priority queue that has, I don't know why I picked that order. And then after that, you can just keep popping out the minimum element from the queue and then putting that in its proper place. And then I think the signal for like using it, the possibility of using a priority queue here is just the fact that like we want things to come out in a certain order, and here you'd use the min priority queue with the comparative to make sure that, because you want to have the element that goes in the first place, the minimum element.
Mm-hmm. I'll also add that the big giveaway for me to use a priority queue when I thought of this problem was actually the complexity. And that's like, that's something that I often have found, like, especially I was working through a lot of these problems last night, and looking at the complexity and just kind of thinking about what solutions might work based on that is actually one of the most helpful things in my personal opinion, right? So having basically log of anything, like some like n times log d or something like that, having a variable times log of a variable really signals to me that it's either going to be sorting or a priority queue. I can't think of much else that any other data structures we talked about that involve logarithms in their complexities like the priority queue or like sorting does. Yeah, so definitely look at both the time and space complexity to kind of brainstorm what kind of data structures or algorithms you'd want to use for your solution. Cindy, worst case, I would say. And sorting a PQ of D elements takes O of log D time. PQs aren't sorted, so I'm not sure if I understand your question exactly. Elizabeth, STL sort is n log n time.
Yeah, I think for priority queues, the popping and pushing is going to be log of whatever number of elements are in that priority queue. So then that's the thing that would signal like maybe I should have a priority queue of D elements, and then I'm like popping or pushing n times. So for the priority queue solution, it's O of n log D, because at any given point, so it's true that a priority queue will have D plus 1 elements, not D elements, but that's still on the order of D elements, so that's okay. And so then every time, as we're iterating through it, we had to, at any given point, we would pop once and push once from a priority queue of like on the order of size D, and we ended up doing that n times because we ended up putting all of our elements in that queue, and then we had to pop them all out one at a time. So then that's comes out to n log D. And we also, for a lot of them, we also had to push as well as pop. But then that would just be like, in terms of the number of pops and pushes, that's just like 2 times log. If you want to be exact, it's somewhere closer to 2 times log of n plus d, but if we're talking just asymptotic complexity, that's n log d. Yes, exactly. Motion
I think,
property
yeah.
log d, and you do that n times.
In the interest of time, I think I'll take over and maybe follow-up questions in the chat.
Yes.
Okay. Okay, so it looks like the next question that we have would be merging intervals. So yeah, this one's kind of cool. I think it was actually merging lists before, but while Elmore was presenting it, someone else voted. So, okay, actually I liked merging lists more, but merging intervals is all right too. Yeah, let's talk about this one. So given a collection of intervals represented by a vector of basically of these interval objects, we want to write a function that merges all of these overlapping intervals. So in this example, we have 4 intervals. I'm actually gonna talk about like kind of what I would do. I did this problem last night, and what I thought of when looking at this was I thought of these intervals on a number line. So definitely a general tip that I would give out would be to like think about the examples and how you arrive at those examples, like the answer for those examples when looking at the problem statement, right? So I literally would draw out a number line like you think of, I'll draw it in black, I suppose. So we have like 0, 10, 20. And then we have intervals from, we have 1 to 3, 2 to 6, and we have 8 to 10. Oh, and also 15 to 18. So that'll be like right around here, right? So yeah, the reason I'm doing this is to kind of see what's actually going on in this example. And I literally did this last night. I drew out this exact number line. And I see, so how do I determine if an interval overlaps was basically the question that I arrived at. And I thought that would be key to solving this problem. So does anyone have ideas on how to determine if 2 intervals overlap? The end of one is after the beginning of the other. Yeah, exactly. Cool. And that's exactly right. So, okay, and then the next thing I looked at was the complexity. So I saw we have an O of n log n time complexity and O of n auxiliary memory. So n log n, as I said like 5 minutes ago, that signals to me either sorting or priority queues. And the one that stuck out to me here in this case was actually sorting. So I also actually thought of a problem from EECS 203 that was kind of similar. So back in EECS 203, we talked about this interval scheduling problem. And basically the key to that is you want to think about problems n times. I don't remember the exact details of the problem, but I remember that looking at the n times of intervals was very key to that problem. So similarly, I thought of, okay, well, one of the ways that I'll be able to compare intervals is to actually sort them by n time, right? Because that's the idea of this number line essentially. So like to figure out that these go together, like these 2 guys here, it's easiest to compare them by if they're right next to each other in our vector, and we can do that by looking at the n time. So what we want to do then is, so my first idea was to sort these intervals by n time. Unfortunately, these are structs, so we kind of need a custom comparator here. So that was my idea. So I would actually write a helper function called, so I would do, what would I do? I would do struct comp by end time. And then I would do, just a typical comparator, bool operator, oops, operator, double parentheses, and then we have interval objects, so capital I interval, right? And that's it. That's our struct, right? So, okay, that's how we're gonna sort these intervals, is with that structure. So what we're gonna do is say standard, or I guess we don't need to do that. The standard library is already, we're already in that namespace for the sake of these problems. So we just say sort vec dot begin vec dot end, and then I name my structure comp by end time. And make sure that you have these parentheses here to actually instantiate a instance of that structure. So if you didn't have these parentheses, you wouldn't compile. Although I should say that we probably wouldn't take off points for that because we don't care too much about compilation. We care more about the actual ideas behind your algorithm. So anyways, what do we do after we sort? Well, after we sort, we just want to basically build up this output vector, right? So, and that's where the O of n auxiliary memory comes from. You don't really need a data structure for this. You really only need the O of n, at least for this solution. You only need the O of n memory for the actual output vector that we're going to have. So, okay, so the way that I thought to do this was to simply make a whole new vector. So I'd have a vector of intervals called out. And I would simply populate it with these merged times. So how would I do that? Well, the where I would start would be to just iterate through my initial vector. So I would say, I thought the cleanest way actually to do this would be to just do a range-based for loop. So for auto, and that'll just get me each interval one at a time. Okay, and as I'm iterating through it, I would say, oh, whoops. So I'd say, well, if out is empty, or as was said in the chat before, the way we compare intervals to see if they're overlapping or not would be to simply compare the start of one and the end of another, right? So if the interval that we're looking at, if the start of that is greater than the end of our previous interval, of our previous latest ending interval, then we know that they do not overlap. And because we know that our vector is sorted, we know that all the following intervals will also not overlap. So what I said was if out is empty or interval dot start is greater than out dot back dot end. So what this is saying is I'm basically building up this vector. If we go back to this graphical example, I think that'll help. So at the very beginning, right, our output vector is going to be empty. So we want to kind of make sure that we at least populate our vector with one thing before we actually make any comparisons. So that's why we have this statement right here. Otherwise, though, we will make an overlapping interval if it's greater than out.back.end. Okay? And if that's the case, then I'm going to say back dot push back interval. Or sorry, not back. That should be out. And otherwise, I'm going to update the interval, right? So that's like this case right here. If they do overlap, then I'm just going to merge these into one big interval. So I'm going to say out.back end equals max of back.back Okay, and so this back. Yeah, so Cindy asked, will out.back.end throw an invalid read or access if out is empty? So I made sure to have that case right here to check if it would be empty. Now, this is, I think, close to a solution, but I actually don't think it's quite complete yet because, so let's say hypothetically, what if we had another guy like right here? So we just had another point right there. Say this is an interval, or I guess I'll make it an actual interval, right there. So what would happen in this case is I would create this interval. So I would have like in my out, I would have what? I would have 1 to 3. And then I would have this guy, which is like, what is that guy? We'll call that like 4 to 5. And then this guy, this third guy, right here, would only get merged with that 4 to 5, when in reality, we should be merging the 4 to 5 and the 1 to 3 together. We should be merging all of those, right? So our solution right now doesn't account for that, because we would only be merging these two, right? Do you guys see how it only accounts for that? Yeah, cool, okay. Okay, so then what we can do is we can basically just merge as far as we need to. So what we'll do then is we can change, basically, what we want to do is change the if, or well, really just this else clause. We want to kind of make it a while loop. So what we can do is say, we're going to say while basically the idea is while we have something to merge with. So do you guys have ideas on what the explicit condition for that would be? Okay, so we have one. While interval.start is less than out.back.end. Yeah, that's the right idea, except I think after we've merged, essentially, we're going to want to look at, we're going to update the back, and then we're going to look at the back. So that's not exactly what we want in this case, but the idea is there, right? Where we're just checking the back. So what I'm going to do instead, actually, is I'm going to move this while loop, just because this is a way that makes sense to me. I'm going to do this first one, and then now the back is going to be updated, right? And then all we want to do is compare the back to the one right before the back, and just do that over and over, essentially. So I think the way that makes most sense to me is going to say while out.size is going to be while it's greater than 1, right? Because if we're only going to be needing this while loop if we have at least 2 intervals. And out.back dot start is less than or equal to out at out.size minus 2 dot end. Then I'm just going to merge these same things. So I'm going to need some more room here. And this is just a one-liner once again. So we're going to say or is it a one-liner? No, we're gonna have to pop back and then merge again. So out at out.size minus 1 dot end equals max of vec oh, and I realize now that this should have been out, right? And this likewise should compare the back of out and the second to last element of out. So we're going to say out at out dot size -1 dot end, and out dot back dot end. And I think that'll work. Oh, and of course we'd want to say out dot pop back. So, yeah. Hopefully that works. And then would be the closing brace for our function. I'll write it in.
Hey, Gabe.
Mhm.
There's a couple questions from the chat. First of all, you missed your return statement, which just return out.
Yikes! Yeah, this is a non-void function.
Yeah, just got a little cram. That's okay.
Yeah, I'm very much on room. So, yep.
And then the other one is it's a lot more intuitive for some people to like sort by start time. And like you can start by end time, which is like is what you do, but could you explain a little bit how that works a bit more? Maybe just another example.
Yeah, so I thought to sort by end time, just because that was kind of the honestly, I was very much motivated by the example in EECS 203 where it's basically this interval scheduling problem where you only get the optimal interval scheduling if you sort by end time. And I know this is a very much different problem, but that was kind of my inspiration for going off of that. If you sort by start time, would it also work? Let me think about if it would. So
I can help you with it. It should. I'm pretty sure the example that's going to be released later today sorts by start time. Like if someone wants to hear their answers to that later, they can also do that.
Yeah. So yeah, this is how I walked through it, and if it does work by start time, and if the answer is sorting by start time, that'll be totally fine as well. So you're saying to walk through kind of how this would work though?
Just someone asked if you meant to sort by start time, and I said no, and that you can do it by starting by end time, but I just thought maybe you could clarify it. But if you think it's clear, then totally fine.
Yeah, yeah, it should be fine to sort by end time as well. But yeah, you can certainly adapt this to sort by start time. Will some of the solutions that we did exceed the line restriction count? So this solution does not. This is like 1, 2, 3, 4, 5. This is like 14 lines. So lines that only include a curly brace, such as like this one, you know, those don't count as lines. Yeah, it's literally just lines, actual lines of code that count as lines. So if you're not counting curly braces for this one, it's going to be 14 lines, which is under the limit of 20. Okay, we can talk about follow-ups in the chat for this one, probably. And then, yeah, I'll probably just answer yours in the chat in the interest of time, Justine, and I'll move on to Eleanor.
Yeah, so I think we have time for about one more question, and it looks like there's a lot of interest in the inverting parts of a separated vector question. That was the spring any question. So start presenting. Yeah, okay. So yeah, this is actually the question that I did for my midterm for 281. I think the hardest part of this question is honestly figuring out. I think like once you figure out the idea for how to do it, the implementation of that idea is relatively straightforward. I think figuring out the idea is something that just takes like just, and I think, and this goes for general questions, a lot of times when you're like looking at a question, you're trying to wrap your head around like what it's asking and the best way to go about it. The best thing to do is just to write down some examples and come up with some ideas for how you might get from the input to the output that you want, and then see how it works with those examples. And so here, for this, the idea is that for one, like if you invert a section of code 2 times, then you'll come up with, it'll give you back your original section of code. And so the idea here is that we can take each chunk that's between the separators and invert it once, and then we can invert the entire vector, and then we will get something that is just inverted by chunks. So just to give an idea of how that would work out, so say we take our input vector and we invert each, oops, am I reading here mistake? And we invert each chunk. And then if we invert the entire vector, then we get something that is exactly the output. So yeah, so 123, so like 123 here, 321 here, and then you can walk through that to see like that by inverting each individual chunk, you just get something that is the inversion of the entire output vector that you want. And so then to implement this, what you can do is you have, so you can have a begin iterator that points to vec.begin, and then I think you would have an end iterator that also initially points to vec.begin. And then you would want to do one pass through to invert each chunk, chunk by chunk. And actually, I'm going to come back to the while condition. I think that'll be easier to come up with once we've written the code inside there. And so here, then we would have another while loop. So the idea is that we want to figure out, so right now, both of our iterators are pointing to the start element. So we want B iterator to point to the beginning of a chunk and E iterator to point to the end of a chunk. And sorry, we want E iterator to point to just past the end of the chunk. So we want E iterator to point to the first separator that we encounter. So then we can, this is just to find where E iterator is supposed to go. Okay, so so after the end of the second while loop, EITR should be pointing to the first instance of separator. And so now we can call invert. And then we would set. So then we've inverted like the first chunk, and now we want to set EITR to point to the place. I think we would actually set both of them to point to the place right after that separator. So then we say EITR is equal to and so I have the prefix iteration. So now, so I'm iterating. So I'm making EITR point one farther, and then setting that to be EITR. And so I think then here we can. Oh, I think. And I think in the while condition, we want to add one. So in our inner loop while condition, we want to add one more condition to say that it's also not equal to the end. Actually, I think we would want that condition to go first, and to make sure that we're not accidentally dereferencing something that points past the end. Yeah, because you're not guaranteed that it will like always end with a separator. And yeah, I think, and this also can give some idea of like the process of how it might be when you're writing out your solution. So like, as I'm writing this out, first I was mostly thinking about like what it would look like at the beginning, and then I finished writing, and then I was like, oh wait, but what if like once you get to the end, and like then I looked at the end and I was like, wait, no, it's not always going to be a separator. So it can be this sort of process. And then also like, since for this exam you can be typing out in code, it's a lot easier to like edit it and go back and fix things when you realize there's a mistake. So I think actually here, the while condition, the outer while condition can be either one. So I'm just going to say, well, either I don't like that. Okay, so then this has taken care of inverting each individual chunk, and then now we're just going to invert the entire thing. Yeah, and so then now I'm going to go ahead and walk through the example, and this will also help serve to double check my code. And so what would happen, I'm going to erase this, give more space. Yeah, okay, so then we would have, we start off with EITR pointing, BITR pointing here and EITR pointing here. Then we increment it. So each point, it's not the end and it's not the separator, so we keep going. But here it is the separator, so then we stop our increment. And we now have the iter pointing here. Remember that the invert function takes in an iterator, that beginning iterator that's inclusive and iterator that's exclusive. So then we invert this chunk, and then we set E iter pointing here and B iter pointing here. And then we do the same thing with the next chunk, and we would wind up with E iter and B iter pointing here, and then that inverted. And so then we would say E iter is not it's not the end, and it's not separated at 21. Here it's at the end. So then we would want to iterate. So then we stop because the iter points past the end, and then we invert this section. And actually, and then, so I said that normally, so I said that then we would say like B iter points past the end, and E iter points past the end of what they used to be, but yeah, looking at this end condition, realize that this is not always going to be this is not always going to work once you get to the very end, because here E iter is already pointing just past the end, so we don't want to increment it any more than that. So actually here, so I'm going to modify my code slightly and use a ternary operator. And here I'm going to say I want to check if E iter is, it's not equal to vector end, then we can do what we said before, it's just increment them both. Otherwise it is equal to vector end, and so then we just set that equal to vector end, and we're at the end there. And so that the idea here is that, so for like any other case that we've been talking about where like B iter is there or it was there, then we want to set E iter to be one past that. But in the case when E iter is already the end vector, that's when this condition here fails. Then we just set B iter to also point to the end, just past the end, vector end. And then we get to the beginning of the while loop, and B iter is vector end, so we exit this. So then we exit this while loop, and we go to this step now. Yes, and Elizabeth, you can also start with inverting the entire vector and then invert each chunk. Both ways work. I just still don't understand why the vector is reversed after the chunk. So why do we invert the whole vector at the end? So what we've done in just this part of the while loop, we have a vector that's looking something like this. And this vector is like, we're not quite done yet. We want to, we still have a little more work to do. But like if you try inverting with this entire vector what we have here, so at the end we have 123. So then, and if we invert the entire thing, we get 123, 321, 777, 9, 10, 11, 99, 777, 1, 2, 3, 4, 5, and that gives you what that what you want at the end. So okay, how do you know to do that? Can't tell from the problem statement. I think here, like there's some problems where you can't just like immediately, and if the other two eyes want to jump in and say like how they like clued them into the solution, and also feel welcome to do that. But for me, as I was like solving it, this is something that came sooner after I saw examples. And I think also like what I said at the beginning about how if you invert a certain section twice, then you get back the original section. That's also key, because I think, so I guess based on the problem statement, you know that you'd have to invert the entire thing at some point because you're inverting the chunks, and like this, you can't get to the final solution and invert anything less than the entire problem, because like 321 at the very end, it winds up really close to the beginning. So I think you can also think of it as like wanting to invert the entire thing, and then you fix all the individual chunks by inverting like each individual chunk, and then by the fact that it's been inverted twice means that it's restored to what it originally was. Yeah, so I guess for the problem statement, it says invert the vector chunk by chunk around the separating vector. Yeah, like Gabe said, I think this is the kind of problem where you really want to make sure that because I think it's also difficult sometimes when writing problems, it can be hard to write everything out in words like precisely what you want to do. So I think a lot of times, like you can also rely on an example to get your point across. So then, yeah. So if the problem is ambiguous, like look at the example and understand what the example is showing you to do, and then do that. Is there any clarification on this exam during the spring? I think like in general, you can make a Piazza post and ask for clarification.
Also, Eleanor, there's a question in the chat to explain the complexity of the solution.
Oh yeah, sorry. I saw that and then got distracted doing something else. So the complexity, so obviously the entire invert is going to be, it asks for complexity of O of S, where S is the distance between end and begin. So obviously this has complexity O of S because it's between begin and end. So this has complexity. When we call invert, by calling invert on all of the individual chunks, that has complexity of the chunk size. So we call invert on chunk 1, that has complexity of the size of chunk 1. We call invert on chunk 2, that has complexity the size of chunk 2. We call invert on chunk 3, that has complexity the size of chunk 3. So if you like sum up all the times when you call invert on a smaller chunk, then that comes out to a complexity of about O of S. And so then overall, I think your invert would take up like about O of 2S, which is O of S. And I think that's also another thing to think about, like having a nested while or for loop. That doesn't necessarily mean that it's like you're multiplying the complexities of the of like the inner and the outer for loops, because I think you also need to look at like how much you're jumping ahead each time. And so in this case, you're not like in this case you're only calling invert on on like a bunch of the parts of the vector. So then then it adds up to like in total only inverting like the entire vector or so. So Elizabeth asked, when you do b iter equals plus plus e iter, does that also change the e iter to point after the separator? Yes. Yes. So that is a prefix increment. So then what this does is it first makes e iter point to just after the separator and then copies that over to b iter. So then b iter points just after the separator as well. In terms of strategy for complexity, would you recommend planning out and considering complexity first, or is the requirement generally based on an intuitively good solution? Yeah, I think here, honestly, I'm not sure which one would come first. I think for me, and like again, please jump in other eyes if you want to say. I think for me, I was just like, how in the world do you like invert it chunk by chunk and like leave the individual chunks untouched? So then I just looked for a way to do it, and then checked that my way was still O of S. I think it's also like it depends on the complexity given. So I think there's certain complexities, like Gabe said, that signal a certain approach. I think in this case, the complexity is maybe doesn't give quite as many clues, and you also want to make sure that like you are giving the correct answer. So in this case, maybe, yeah. Again, if someone else wants to say an answer, I'm having a hard time picking one that like generally always knows.
But if you want, I know on my exam there was like a quick and easy solution that just like objectively had like the worst, like didn't have the right time complexity. So like something was like, I don't know if it was like O of n log k, or like they add that second thing. Like a lot of times you can think of a solution that's O of n log n, or like O of n squared, and it can be super easy to think of and you can get it right away. But like if you don't get the complexity, you're gonna lose points. So like it depends. Like in this solution, I agree with Eleanor that like I probably would have started with how in the hell am I gonna do this and like start from there. But like in the general case, I definitely consider complexity when doing my solutions, because like you have to find a solution that has that complexity. And a lot of times that's like what they're testing for, is like if you can actually make your solution reach that complexity. For the more complicated questions like these, I think they mostly just want to make sure you do it. But like a lot of the questions, you can think of a really easy way to do it that's just going to have the wrong complexity.
So to Jacob's question, who's asking about O of S for invert, and that might get a little bit confusing because you might be like, well, this thing doesn't, the complexity doesn't involve S at all. Like, where does S come in? I guess I think of invert as, I mean, S is strictly smaller than N, right? And there are a certain amount of chunks, and we're just going to invert. Essentially, we're going to invert each chunk twice, kind of, right? One time chunk by chunk, and then at the very end, we invert everything all at once. So because all of the chunks basically add up to n, excluding the separators, I guess. So all the chunks essentially add up to n in their size. You are doing like this O of S operation, multiplied however many chunks there are, and you can kind of think about like if you let S be, I guess, just assume for simplicity that S is the size of every single chunk, and there are like, I don't know, T chunks. So you know that S times T is equal to N in this case, right? Because there are T chunks of size S, and that's basically the whole vector. I hope that helps with where S kind of comes into the equation here.
Maybe if one of you two could answer Justine's question about complexity or accuracy, because if you have more experience like coming up with the rubric and grading the question.
Yeah, so always try to do the right answer, like get as much as you can of the correct complexity. Yeah, maybe Dr. P didn't say it in your guys' section, but when I took the class, Dr. P said what I just said, because if you are off in complexity, where you're going to lose like 75% of the points, just guaranteed. If you have the right idea, but it's incomplete, then it's unlikely that you're going to lose that many points.
Oh yeah, and I will also say this is, I think when you're doing the 281 written problems, sometimes like you can get to the question and you can be like, I have no idea how to do this. Like this seems like it relies on like this certain trick that I just can't think of under this kind of pressure. And but I think a lot of times the rubric is like that little trick that it relies on is like actually probably going to be like a small part of how much the question is worth. So the idea is that you just want to like write as much of the solution as you can. So maybe you can say, well, I don't know how to do like this part of it, but I know that you start with this and you end with this. So then you just write out the part like I start with this and I end with this. And if you don't like get the trick, well, you'll get credit for the rest of it. So just like don't waste a lot of time just like agonizing over how like you don't know like exactly how to do it, but just like make sure you leave enough time to just write down what you have so far, just as much of an outline of the question as you can write out, and you should still get like a lot of the points. And then like Gabe said, do try to make that the correct. So like, what if like you can't think of the trick that makes it the right complexity, but you can think of the naive solution? Well, write out as much as you can of like the rest of the outline of the solution that would be the correct complexity. I think I had experience with this both ways. I think there was my final exam for 281. There was one question where, actually both questions, I couldn't think of the trick. And one question I thought of a way to do it with the naive solution, and the other question, so I ended up writing out the naive solution. And then the other question, I spent like a long time trying writing out different things and trying to find like how am I supposed to do this, and I couldn't think of how to do it. And then I got to the end and I didn't have time to write out all the parts that I didn't know how to do. And had I written out all the parts that I didn't know how to do, I would have gotten more points on the question that like I wrote out like an outline of the solution with the correct complexity, as opposed to the one where I got like accurate and but with the not correct complexity. Someone wanted to talk. Do you want to talk about percent of the greatest time complexity and correct implementation? I think it depends on the rubric for that question. The rubrics I don't think have been set yet. I guess Gabe or Danny, if you have like a general idea of how it generally goes for implementation versus time complexity.
So we kind of break it up piece by piece in terms of like what part of the correct implementation you got, and sometimes there are multiple correct implementations, so that obviously would change things. But like I'm looking at our spring exam, for example, and yeah, we just kind of break it up in terms of like what part of the correct solution you got. Because for example, this one that I'm looking at, it only has one correct solution, so that we found at least, and that all students found. And so you just get like some points for each kind of correct big idea of the problem. And if you miss that big idea, then I guess you're going to lose most of the points, right? And so if your complexity is off for this problem, for example, you're going to lose most of the points, basically. Like I said 75%. So like, yeah, if you have a correct solution that is over time complexity, you can probably expect to get like 25% credit.
On my exam, both the questions just like they're about like 20 points, and they take away 6 points if you overtime or memory. So if you're overtime and memory, you would lose 12 points, which is over half the points. Like when I took winter.
Okay, so maybe a little less than 75. You would lose.
I think it like varies. Like it's hard to give like a quick. I think it varies, but like I remember when I took this exam, like I was like, what will happen if I'm overtime? And they were basically like, just don't be overtime because you're gonna lose points. And it's very easy for them to just be like, no points for like they can debate whether or not you like your solution like certain lines of your solution can count towards certain things that they give points to. Like it's very easy to dock points for time, and like they're usually like pretty aggressive.
Yeah, I think for me, when I mentioned where I had written out the naive solution, I think I lost I got like points for like a correct for like getting the correct answer, but then I lost like 8 points for it not being the correct complexity, and then like points elsewhere for not correct memory. I think, yeah.
Yes, test. So O1 extra space means you can declare anything that has constant size. So yeah, you can create an iterator, an integer. If you want to declare a constant size array, for example, that's fine too. Like you remember from the anagram problem where you were limited to 26 characters, you had to declare an array of size 26 for every ASCII character, every lowercase ASCII character. That's also O1. So if you basically anything that has constant size and as you scale up the input does not change in size.
What other questions do people have? I think we're not going to go over any more written questions because we're past 3 when we said we'd end it. But like, if people still have outstanding questions, happy to stick around for a little bit longer and answer those questions.
I would be willing to go over one more because
Okay.
I don't mind. I'm bored. So if people do want to talk about another question, I'd be willing to go over one more. Can we do the water problem? Yeah, why not?
That one's a good problem to go over.
Yeah, I like that one.
I think that one has some good things that are like general patterns that you can like add to like your toolkit of possible problems that it would be.
Sure. So I can, yeah, I'll take over and talk about that one. But yeah, if Eleanor or Danny, you guys have somewhere to be, please don't feel forced to stay.
Yeah, I think I might actually hand over hosting to you and head out because I actually have quite a bit going on this weekend.
Okay, no worries.
And I think, the only thing is I'm not quite sure what that does to the recording if I hand over hosting to you and then leave.
I'm hoping I can just stop sharing or stop recording. What?
Yeah, I think I clicked that it saves to my computer. I'm honestly not quite sure how that would work. Start by making you host. Yeah, and I guess if there's any issues with the recording when I try to leave, then they can just stay in the call, but I probably won't be answering questions or looking at the chat.
Okay.
I
Yeah,
think,
no worries.
actually, I think I'd feel safer doing that. So I will still be in the call, but I will not probably be paying too much attention because I do have other stuff going on.
All right. Anyway, so yeah, I'll get into the trapping rainwater problem. So, okay, yeah, this was a tough one. This is probably one of the harder ones on the practice problems. And yeah, you're not really using any data structures. It's kind of an interesting one. So the idea here with trapping rainwater is that we have this vector representing the height of these tiles, I guess. So like this corresponds to a tile of 1 tile, 0 tiles here, 2 tiles here. And we're asking, you know, we have these blocks of water. We're asking, where can water fit? So where can water fit in without, I guess, kind of overflowing over the tiles to either its left or its right? So the thing that comes to mind for each of these guys is we want to have some kind of enclosure on both the left side and on the right side, right? So like for this piece of water, we have an enclosure on the left and the right, and you know, for all these waters, it's enclosed on both sides. So the fact that we're looking at both the left and the right, it wasn't immediately obvious to me, but eventually it kind of came into my head that what we want to do is have 2 passes, one from left to right and one from right to left, right? So, and that will kind of get us the maximum enclosure height at each, from each direction, right? So what we want is we want to know where are we going to have, I guess, at each particular index, are we going to have enclosures on both sides? So the way I did this, which may not be the most efficient in terms of like number of loops going through, but I did it with actually 3 passes through the vector, which is fine. It's 3n or O of 3n, which is really O of n, just still O of n. So how did I approach this? Does anyone have ideas that they'd like to discuss in the chat? If not, that's okay. All right, so what did I think of? I guess another thing I thought of just in terms of test taking strategies and while I was working through this is I thought of other examples too. So I drew this example out. So let me use the same color. So I had like, let's say we had this. This is a completely different example, like separate from the actual one given. So I thought of like, what if we had something like this? So 3, 2, 1, 0, and then 1, 2, 3, right? So we know that water is going to go in these spots, right? We're going to have water looking like that. So again, I thought of like, how on earth am I going to figure out that like at each index how much water we have? So what I did is I thought of how much, like what the maximum enclosure size is coming from the left and coming from the right. So for example, when we're here, let me change this. When we're here, the maximum enclosure from the left is of size 3, right? And the maximum enclosure from the right is also size 3. And our current height is 2. So we have room for 1 piece of water, essentially, 1 block of water. Likewise, if you look at it from this middle one, our maximum enclosure size from the right is also 3, and our maximum enclosure size from the left is also 3. And because the height is 0, we have room for 3 pieces or 3 blocks of water, right? So is that making sense so far? How we're kind of looking at it from both sides? Is anyone still there? Okay, cool. So the question becomes, with this idea, how are we going to implement this? So Justina is saying, so it's determined by the min of the max of L and R enclosures. Yes, exactly. So, okay, how are we going to do this then? Well, what I did is I basically, like I said, did 2 passes through the array. So yeah, I'm going to get into writing the code here. To make 2 passes storing the maximum left and right enclosures, I basically made just copies of our, I said array, I meant vector, same idea. And to do that, I had to store a variable called running max. Right, so I have my running max variable, and what I'm going to do is I'm going to say, I'm going to declare these 2 vectors. Or actually, I'm sorry, we can't declare vectors because this is O1 with auxiliary space. So we can't do that. We have to actually do it all in place, which is totally possible. So what we're going to have to do is, instead of having 1 running max variable, we're going to have 2. So we're going to have running max, I'm going to call it forward and backwards, right? And I'm now realizing that because I don't have these vectors, you can't do it with multiple passes, really, or it doesn't make sense to. So this is good. I'm doing this kind of on the fly. So we're gonna do, but this is fine. We're gonna do for we're just gonna iterate through the vector and go from both sides, essentially. So let me think about how to do this coming from the left and from the right without any auxiliary space. We might still have to make multiple passes over it. Hmm. Yeah, so the idea I had before was to store the whole vector going from the left, with all of the maximums leading up to that element going forward, and all of the maximums going up to that going backward, and then essentially taking the minimum of those and then subtracting that from the current height of the block. But because I'm doing this on the fly and I don't want to have to think for too long, I might have to refer to our solutions real quick, just for a moment. Right, so, okay. We have to keep track of this running max coming from the front and from the back. And then also we're going to want a total variable to just store the total amount of water. So int, I don't know, I'll just call it total for the amount of water. And actually, because we're interested on keeping the number of lines of code small, what we want to do is have this probably all on one line. Total. And then we're going to have indices for where we're at in the left vector and for the right vector. Or sorry, not for the forward traversal and for the backward traversal. So we're going to have, I'm just going to call them, I'll just put it on 2 lines to keep it clean. Okay. And so instead of a for loop that traverses through the whole thing forwards, what we're going to want to do is actually use it, do this problem using our 2 indices. So we're going to be kind of moving forward or backward depending on which condition we're in. Oh, are you not able to see what I'm sharing?
No, it still just says int running max forward and then like backwards and then the for loop.
Oh no.
It doesn't look like it's updating.
That's interesting. Let me stop and restart. Oh yeah, it appears it lost connection for a moment. Like it's, oh, now it should be there. Yeah, for some reason my iPad wouldn't connect to my laptop, but we're back. We should be at least. Okay, so anyway, what we're gonna do is go from forward and backwards. So we're gonna say while so we're basically, again, traversing from each direction, and we're going to stop once the 2 indices meet. And of course, you could do this with iterators as well. So, okay. And then we just have essentially just a set of conditions. So we're just going to compare the heights of the vector at each index. So if So if our height at the forward index is less than the height at the backward index, and also I need to make sure to declare these variables. So we have equals 0, backward index equals back.size -1. So if we're in this condition, then what we do is we actually compare the maximum heights. So this is the part where we're deciding what the maximum enclosure height is on each side. So if and these should also be 0. So if running is less than my vector at the forward index. Oops. Then what we're going to do is update that maximum. So and alternatively, what you could do is you could actually reduce these two lines down to one line. I'm going to change the colors for that. If you want to save lines, what you could do is say running max forward equals max of, I'm just going to say RMF for running max forward and back at I for the index, right? So that's just the idea that you can save lines by just reassigning it to either itself or back at I if it's bigger. And that's helpful for saving lines. But I digress a little bit. Okay, so then, otherwise, if that's not true, if we're not updating that that running maximum, then we know that we might have room for water, right? Because we're not updating it, so that means the height is smaller than the current running max, so we know it's going to be able to be enclosed on the left side. Okay. So then what we do is we say else and then lastly, we have to, only in this case, increment the left index. Or sorry, not the left index, I'm calling this the forward index. And so that'll complete this if block. And then the other case is, so else, I don't know if it's worth going through because it's really just the same idea, except everything is reversed, right? So we're instead saying if the backward index is greater than or equal to, then we're going to just change this to running max backward, forward, and then backward index. Everything, pretty much the else clause is exactly parallel to this in terms of, you know, we're just going from backwards instead of forwards. So I'm just going to say that. And I hope that makes sense, right? And then looks like we have some questions that Danny was answering. What if the left block is taller than the right one? So we're keeping track of the maximum at the, yeah. Can I go through one iteration? Yeah, I think that would help a little bit. So we have these two indices. I'm going to go through this example. We're going to start here and here. And then we're going to say if vec at forward index less than vec at backward index. Well, that's not true. So we're going to go into the else, I suppose, at this stage. And so the else would say if running max backward is less than vec at backward index, then, oh, really? I probably should have set the running max forwards and backwards. Is it okay to set them to 0 rather than vec at 0 and vec at vec.size minus 1? It should be. So yeah, it is fine. It is fine. So what we're going to do is we're going to go into this else clause, and then we're going to say if running max backward is less than vec at backward index. So I'm going to say running max backward. I'm just going to call it RMB equals 1. And that's it. Okay, and then next iteration, I'm gonna move this guy, or I'm gonna go into this clause. Then how do we account for the intervals in between? Yeah, so the iterators are going to get closer as we loop through. And then we go into the same thing. So now that our running max backward is equal to 1, it's no longer going to be, this condition is no longer going to be true, right? So because our running max backward is 1, we're going to go into this, we're going to be looking at this same thing again. We're going to go into the else clause again on this next iteration. And then now we go into the else clause. So we go into basically this parallel clause on, within this. So now we're essentially saying how much water are we going to add to this block? So because it's exactly equal to running max backward, we're not going to add any water here. And so that's fine. Then what we're going to do is we're going to end up going into this guy. We're going to basically do the exact same thing. So we're going to go there. And then when it really gets interesting is once we get to looking at the next iterator or the next indices. So after we've decided that we don't put any water in the first block and the last block, our iterators are going to be updated to the second and second to last block with the same value for the running max. So now because our forward index, or the vector at forward index is 0 here, and the vector at backward index is 2, we're going to go into the original, this if clause. So this is where it kind of gets interesting when we actually start adding water. So our running max forward is 1, our running max backward is 1 at this point, because we haven't actually updated this yet, but that's okay, because we know what our maximum, or basically what our limit is on the left side, because our limit is running max forward, which is 1. And so we go into this else clause where we say total plus equals running max forward minus back at forward index. So basically that's saying it's equal to total is going to be equal to total plus 1 minus 0, which is just total plus equals 1 at this point, right? So our actual total is 1. So Justine is saying, I thought information on both the left and the right side of each interval is needed to determine the amount of water that can be held. Yeah, that's exactly right. But it's what determines the amount of water that can be held is the minimum. So we have all the information we need on the left side. When we're looking at this piece of water right here, we have all the information we need about the left side. So if the left side is smaller, the running max forward is smaller, then we know that that's like our kind of, I guess, limiting factor here. And that's why we're confident that we can go in and add this water. Otherwise, if, let's say this was like way higher, it was like up to here. If it was up to here in black, just to make it clear, then I know that, I don't know that, I'm not confident about what the limiting factor would be in determining how much water I can put here. So what I'd have to do is I'd have to keep looking at the right, and that's why we only update the right side. Because basically we're trying to find what the limiting factor is, if that kind of makes sense. Well, so we know what it is. We're confident about what it is from the left side, right? Like we know exactly what how much space we have on the left side in this case. Once we're looking at this block of water, right here, and then the only time we actually determine whether or not to add that water is if the we have how do I put this? If we have enough space, or if the left side is smaller, right? If the left side is smaller than the right side, the right enclosure. So otherwise we won't add water until we know that for sure, which is only when the left enclosure is smaller than the right enclosure.
Hey, sorry. Do you mind if I just ask on voice?
Yeah, that's totally fine.
Yeah, I guess I'm just a little bit confused because I see that the strategy is going from like the very beginning of the vector and the very end and then going inwards towards there. But I guess like when you're starting from the left side, I'm kind of confused on how we're able to expect like that interval's right side to be like shorter or taller or whatever, because like if we're starting from the two opposite ends of the vector, then we don't really know information about like the heights in between, right?
We don't know information about the heights in between. Yeah, no, that's exactly correct. So you're saying we don't have any information about like about this region, right?
Yeah.
Or I guess we know about like we know about this much at least. We know about those first two, but we don't know anything about that. So that's why we only go into actually adding this water if this is smaller, right? So we're only looking at potentially adding this water if vector at forward index is less than vector at backward index, right? So in this case, vector at forward index is 0, and vector at backward index would be 2. And so then we're looking at potentially adding that water. And then we only actually add that water if running max forward is less than or is greater than or equal to vector at forward index. So because this guy is smaller than this guy, we can go into this first if, and then we only add that water if vector at forward index, so again, this guy is going to be, let me think about this, is less than or equal to running max backward. So we're confident that it's enclosed on the right side because the current index, the forward index is smaller than, or the vector at the current forward index is smaller than the vector at the backward index. And then we can add it because the running max going forward is greater, so it's enclosed on the left side. So it's kind of enclosed on both sides. Or not kind of, it is enclosed on both sides. Still a little confused. Yeah, I don't blame you. This is definitely a very challenging problem in my opinion. I definitely think I don't know, for exam questions, you kind of saw the pattern on exam questions was definitely, I think, a little bit more focused on actually using data structures, because this problem is kind of, I mean, it really doesn't use any data structures. I think for the exam's sake, like this is like more one of those, I guess, like tricky leak code questions. I think this was actually derived from a leak code question. If it makes you feel any better, I think the exam would kind of be more focused on actual lecture material and lecture data structures. So running max forward, what does running max forward equals vector at forward mean? So that's essentially updating our left enclosure, right? So like I was saying, we're keeping track of how much enclosure we have on the left side and on the right side. So if we find that if we're at this index, for example, let me erase some of this if there's room. Once we're here, right, up to that point, our running max forward is equal to 1, right? But as soon as we get to here, we realize, oh wait, our left enclosure is actually bigger. So because, I mean, after this point, our left enclosure can be bigger than 1 because the value here is 2. So we say running max forward is going to be equal to vector at forward index, which is 2, right? So we update it to 2 once we get here. And then once we get here, we'll update it to 3. Is it possible to just loop from the left, keep 2 iterators, and deal with water intervals at a time when we find a valley? So are you saying we're going to have a left iterator and a right iterator? I mean, you're going to have to move the right interval or right iterator at some point, right?
Yeah, so I guess like the way I would understand to do it would just be to have 2 iterators and then have them both start at the beginning, and then keep one of them on the left side when there's like a block essentially, and then kind of iterate the right one until we reach some sort of max height, and then the next one after that is less. And then that way we kind of know the positions where there's like kind of a valley that should hold water, right? And then deal with the water then, and then kind of put the start and the end iterators at the new kind of height that we start at, and then kind of just iterate through that way. But I don't know if that's like a feasible thing. Because I guess I wouldn't be able to really think of the way of going backwards or going inwards from the 2 ends.
Right.
Exam.
So I am not sure that would work. Because you're saying, yeah, one of those iterators, you're going to just move to find the right enclosure, correct?
Yeah.
Yeah, so you wouldn't know when to stop that right iterator, I think. Right, because to actually be confident that you found the maximum, like the largest right side enclosure would be the only way to do that would be to go to the very end. And if you go to the very end every time you find a valley, you're gonna be in O of n squared time.
I was thinking like every time, like at least in this diagram, every time there's like a, I guess a max, quote unquote, and then the next element like is smaller, then that means that that would be an independent valley, right? Like I'm not sure how the end of it really has to do with it, because as long as, it seems like to me that as long as the next one after the current max is less than what the current max is, then like the interval for the water should be set, but I'm not sure if I'm just understanding that wrong.
Okay, so you're saying iterate until you find something that's greater than or equal to that height to see if we can enclose it?
So basically, like in terms of the diagram above, like we see that we would, for the right one, just iterate all the way to the height of 2, and then say we would iterate one more time and then find that the next one is 1. And so that would be like, oh, so now I know that between that block of 1 and the block of 2, there should be water, right? And then just moving on after that, like starting from 2 after dealing with the water on the first interval, starting from 2 and then going all the way until like the tower of 3, and then iterating after that, it's 2. So we stop there, and then that's another interval. I'm not sure if that's like just because of this example that I understanding it this way, but
okay, so let me see if I follow you. So we're here on the left with one of the iterators, and then we increment the other iterator all the way to here.
Yeah, to there and then beyond one more time, I guess, just so we can make sure that that one's actually less. And then if it is less, then we deal with the one right beforehand, I guess.
So our one iterator is still here, right? The first one?
Yeah, yeah.
I'm not sure. I don't understand why you want to go from the 3 to the 2, like why you want to go here.
Because I guess to guarantee that that's actually where the valley ends, because if the one next to it was actually taller, then, oh, actually, well, it wouldn't matter, I guess.
Yeah, because you already have the left enclosure like set, right?
Yeah. Okay. I guess I'm just like confused because of all the situations where the left could be potentially taller than the right, or the right could be potentially taller than the left, and like where that would fit in.
Yeah, so theoretically though, you're saying we iterate until we find like something taller, like, so like this guy is the first thing that's actually taller than where the first iterator is at, right? So what if we don't find something taller until the very end though, like all the way here? Then we'd have to increment it all the way to the end, right?
Yeah.
Okay, and then we really just wouldn't be sure how to fill everything in between with water.
Yeah, that's true.
So yeah, I'm not sure that would work exactly.
Okay, so like essentially like the only way to do it would be to go from both ends.
As far as I know, yeah. This is
All
a
right.
really tough one.
Yeah, I think I'll just have to think about it more, but thank you.
Mhm. Okay. Yeah, so hopefully at least some parts of this review session were helpful. If you guys have any more questions about, like, general questions about any of the problems we've gone over or some advice in general, although we've covered quite a bit already, feel free to ask. But other than that, I think this is a good session for now.